In this example, we have a heated root that can be defined by this 1D heat equation here. This example has the same boundary condition and initial condition similar to the example 1, where you have the boundary condition here and the temperature is equal to 0 at both ends of the root, and the length is given equal to pi in this case. Therefore, at x equal to pi here, you have the temperature equal to 0. And over here at x equal to 0, you have the temperature U equal to 0. The initial temperature at all the points here will be equal to 100 degrees Celsius. Therefore, you have the temperature at time equal to 0 is equal to 100 degrees Celsius at all the point x here. And the length x is between 0 to pi. So you have the same problem similar to the example 1, just that the length and the initial temperature are provided now. So you want to solve this PDE and obtain the temperature distribution at various x locations at various times. By using the same approach, in the first step you apply the separation of variable method, where you let the solution of the PDE equal to the multiplication of the independent variable here. So you take the x multiplied with the t function. Differentiate u twice with respect to x, give you x double prime t. Differentiate u with respect to t, then you obtain the xt prime. Shift the t to the right hand side and shift the x to the left hand side, then you're able to separate the variable x on one side and t on another side. After you success to separate the variable on two sides, then you let this equal to a separation constant. We are using the negative lambda for this purpose. Don't forget the negative here. If you refer to these two components, then you obtain the first ODE. If you refer to the first and third component, then you obtain the second ODE. After you obtain two ODE from the original PDE, you need to assume three cases for the lambda here. In the first case, we assume the lambda equal to 0. Then you can reduce these two ODE into this format. And you need to use the characteristic equation approach to solve these two ODE. And you should be able to obtain this result for the t function and the x function. So after that, your PDE solution for the first case will be equal to the multiplication of the xt. So after you substitute inside your x and t, then you should be able to obtain the final answer a1x plus b1, where the a1 and b1 are the constant for the first case. You need to pay attention if you have the repeated root. So in this case, the repeated root is double 0. In this case, you will obtain linearly solution where you have the exponential 0x similarly here. So you need to do a treatment by multiply the independent variable, which is the x, to the second solution here, so that this solution will not be linearly dependent to the first solution. For the second case, you substitute the lambda equal to negative alpha square and your alpha is greater than 0. So after you substitute inside these two ODE, you should obtain this. You continue to solve these two ODE and you should obtain this solution. So if you have a root equal to a plus minus real number, then we can obtain the solution in the hyperbolic sine and cos format. Multiply the t and the x solution that you obtain here, you can obtain the PDE solution for case 2, which is equal to x multiplied t. You should obtain this PDE solution and you have the constant a and b for the second case. For the third case, you have the lambda equal to positive alpha square. After you substitute inside here, then you should obtain these two ODE. And you need to solve these two ODE to obtain the corresponding solution. So if you have the root in the plus minus imaginary number, then you know that it can be written in the cos and sine format. So after you obtain the t and x here, take the multiplication between them to obtain the PDE solution for third case, which is this, and you have two constants here to be solved. These are the three PDE solutions that you obtain from these three cases. Let's continue to apply the boundary condition in order to obtain the eigenvalue and eigenfunction for each case. So this is your PDE solution for the first case. Let's substitute the boundary condition. For x equal to 0, you obtain the u equal to 0. So substitute x equal to 0 here, your u will be equal to 0. Therefore, when you compare, you obtain the b1 equal to 0. Therefore, we can substitute b1 inside the original PDE solution here, and you obtain the u1 equal to a1. You continue with the second boundary condition. Substitute the x equal to pi, then you should obtain your u equal to 0. So let's substitute x equal to pi here, your u will be equal to 0. Then when you compare, the x is not equal to 0 here, therefore your a1 must be equal to 0. So you obtain a1 b1 equal to 0. If you substitute inside the original equation, you obtain your u1 equal to 0. Therefore, there is no solution in this case. We do not apply the initial condition in this case because you need to substitute the t equal to 0, but your PDE solution here is only x. Therefore, we cannot simplify it. This is the PDE solution for the second case. Let's apply the first boundary condition. Substitute the x equal to 0 inside, you obtain u equal to 0. So u will be equal to 0 when you substitute the x equal to 0. And you know that hyperbolic sine 0 gives you 0. Therefore, this term can be cancelled. Hyperbolic cos 0 gives you 1. When you compare the coefficient for the exponential on both sides, then you obtain the 0 is equal to a2. Since a2 is equal to 0, therefore this component can be eliminated, and you obtain this solution. We continue to apply the second boundary condition here. Substitute the x equal to pi, you obtain u equal to 0. So u equal to 0 when your x is equal to pi. Compare the coefficient for the exponential on both sides, you obtain 0 equal to b2 hyperbolic sine alpha pi, which is equal to this term. To solve this, you must understand what is alpha pi. So alpha is greater than 0, therefore alpha is positive. So alpha pi will be greater than 0, therefore this is positive as well. It's very important for you to understand the hyperbolic sine will be equal to 0 when the alpha pi here is equal to 0. But this cannot be happen because your alpha pi will be always greater than 0. So since the sine phase here is not equal to 0, therefore your b2 must be 0. So you obtain the a2 and b2 here equal to 0. Substitute inside the original PDE. These two terms can be cancelled. Therefore you obtain 0 for your u2. So you have no solution for case 2. This is the solution for the third case. Let's apply the first boundary condition. Substitute the x equal to 0. Then you obtain your u equal to 0. Cos 0 gives you 1. And sine 0 gives you 0. So this term can be cancelled. So you have the a3 equal to 0 when you compare the coefficient for exponential on both sides. So this is the answer after you apply the first boundary condition. You substitute inside, then you obtain the new PDE solution. You continue to apply the second boundary condition. Substitute the x equal to pi inside. Then your u will be equal to 0. So you need to understand what is sine alpha pi here. So we know that sine n pi can be equal to 0. And we know that alpha is greater than 0. So your alpha pi will be greater than 0 as well. To make the sine term here equal to 0, in order to obtain non-zero b3, then you must select the sine alpha pi equal to the sine n pi here, which is equal to 0. And when you compare the alpha pi with the n pi, then you can see your alpha will be equal to n. And your n pi and alpha pi here must be greater than 0. So from here, you know that your n must be positive. We start from 1, 2, 3 and so on. Why can't you have n equal to, let's say, -2, -1, 0 and so on? Although when you substitute the n to be this number, your sin n pi will be equal to 0 as well. Let's say you choose the n equal to 0 here, so substitute inside, you obtain 0. And this is not equal to the alpha pi because alpha pi will be greater than 0 and is not equal to 0. Similarly, if you have negative integer for the n, so after you substitute inside here, you will obtain the negative pi. This is not equal to the alpha pi here because alpha pi must be positive. Therefore, your integer n cannot be equal to 0 or negative. It must be a positive number starting from 1, 2, 3 and so on. Therefore, we successfully obtain the non-zero B3 when you substitute the alpha equal to n from here. And your n is equal to 1, 2, 3 until infinity. So you can substitute the alpha inside here to be the n. Therefore, this is no longer a single solution. It will be a multiple solution with n index. With that, we successfully obtain the solution for the third case. There is typo here. Please help me to correct this. So your alpha should be equal to n only. Since you obtain the PDE solution equal to 0 for these two cases, therefore there is no solution in case 1 and case 2. No solution for the PDE means there is no eigenfunction and therefore there is no eigenvalue. And you obtain this PDE solution for the third case. And you have the alpha equal to n here. So lambda equal to n squared here is your eigenvalue. And the solution here to the differential equation, which is the PDE in this case, is called the eigenfunction. So this is your eigenvalue and eigenfunction. You can substitute the index n equal to 1 to obtain the mode 1 information. So you can have the corresponding eigenvalue and corresponding eigenfunction here. And you can also repeat the same procedure, substitute the n equal to 2 to obtain the eigenvalue and eigenfunction for mode 2. In fact, all of these eigenfunctions are the solution to this PDE. So if you substitute inside the left hand side and check with the right hand side, they should be the same. Therefore, you obtain infinity solution here that satisfy the PDE. In the step 4, you need to perform the superposition principle in order to combine the individual solution into the total solution. So for the first case, you have 0, you add with the second case, and add with the third case. For the n equal to 1, add with the n equal to 2, and if you continue, you should obtain the total solution equal to the summation of this component from the n equal to 1 to infinity. Don't forget to add the summation term here to indicate you perform the superposition principle. So far, you have successfully obtained the PDE solution in this format, and you see there is still one unknown coefficient to be solved. So we can apply the initial condition here to solve this coefficient. When the t is equal to 0, your u will be equal to 100. Substitute t equal to 0 inside, exponential 0 give you 1. And then you substitute the u equal to 100 here. Then you successfully obtain this equation, where the summation of the b coefficient multiplied with the sign term here is equal to a constant. And you know that your x is within a finite interval from 0 to pi. So this is your tau, which is the maximum finite interval. Your tau is equal to pi. So when you look at the summation sign term here, you can recall the Fourier series expansion technique. Summation sign term here is exactly the half-range Fourier sine series expansion that you have learned before, where you have the fx equal to the summation sign term. Since the summation sign term is equal to 100, therefore the fx is equal to 100. So from the half-range Fourier sine series expansion, the b coefficient here is equal to this formula. And the fx here is equal to 100, so you can substitute inside. So what is your frequency? So your omega you can obtain by compare to these two terms. Since you have sine nx, so when you compare with sine n omega x, then you get the omega equal to 1. Half range extension has the half range period, which is p over 2, or the half period will be equal to the tau here. Since the tau is equal to pi here, therefore you obtain the L and tau equal to pi. So you can substitute here to be pi. So if you continue from here to find the omega, substitute the p equal to 2L here, you obtain pi over L. And then since L is equal to pi, therefore you obtain 1. This answer is same with the answer that you obtained previously. You can use either method to compute the omega. So after you compute the omega equal to 1, substitute inside, you obtain nx only. After you substitute all the parameters inside this formula, then you should obtain this. You need to perform the integration here. So we can take out the constant to outside. After you multiply, you should obtain 200 divided by pi. Then you need to integrate sine nx with respect to x. Therefore, you should obtain negative cos nx divided by the coefficient inside here. So you should obtain this answer, and don't forget your limit 0 to pi. Substitute the limit inside, you obtain the negative cos n pi divided by n, minus with the limit 0 inside here, you obtain negative cos 0, which gives you negative 1. Therefore, you have negative 1 divided by n here. So cos n pi, we know that this is negative 1 power of n. Negative here can be cancelled, become positive. Therefore, you obtain 1 over n minus with negative 1 power of n. So this is the final answer for the coefficient b here. Previously, you obtained the PDE solution to be this, with the unknown coefficient here. Now you success to obtain this b coefficient. So you need to substitute inside, which gives you this final answer. And this is your particular solution. This is the PDE solution and can be used to describe the temperature distribution for this heated room. So this equation is valid for the x between 0 to pi. Imagine you want to find the temperature at the half root here. So this is at x equal to pi over 2. So you want to know what is the temperature change over the time at this position. So you can substitute inside this equation, substitute the x equal to pi over 2, and then the t, you can substitute the t equal to 0 in order to obtain the temperature at 0. So you can increase the t to 0.05, then you can obtain the blue color information, and you continue with 0.35, you obtain the red color information. You can continue to substitute the t equal to 0.6, 1, 1.5, and so on, in order to obtain the temperature change over time at x equal to pi over 2 here. So if you plot the temperature change with respect to time for the point pi over 2 here only, then you get at t equal to 0, you have 100. And then t equal to 1, you have this temperature, t equal to 2, you have this, and so on. And it takes around 5 seconds to achieve the steady state temperature, which is equal to 0 degrees Celsius in this example, since you have the boundary condition here equal to 0 degrees Celsius. If you want to find the temperature distribution at other point here, so you can repeat the same procedure and you should be able to obtain the temperature distribution given in these two graphs.